Hello my friends, welcome again to my video channel. Today we will finalize the development of the design of the output voltage regulation to get stability. I produced this intro after I was ready, so I can tell you what you will see. A change of concept. It was not possible to get a stable output voltage with the power Mosfets. I changed the concept. You see my tries, my errors and my efforts. But finally it was successful and we come very close to the goal that we have a closed case and a working power supply. Let's start. Now I will compare the two types of power Mosfets I have used. My first experiments I made with the BOZ80. I couldn't get the isolated version, the isowatt, so I only had this one with a tap which is connected to the drain. So later I didn't use it, but this transistor has an input capacity of 600. You can see it's 650 picofarad only. This is much less than the other one which I use now. I use this unit, the SPA11, because I got the isolated version, but this one has again an input capacity of 1600 picofarad. So this is factor 2 or factor 3, not so good. And I want to prove that there's a difference in the electrical behavior with this test circuit. I use a square wave generator with 20 Hertz or 15 Hertz, and I use both transistors, SPA11, which is in the moment actually in the high voltage power supply, and the BOZ80. Same schematic, 2 times 270K in the drain, up to 400 volt DC, and the gate is controlled via the 470K resistors. So this is approximately the value which I can reconstruct as a driving impedance in this high voltage power gear. And here I connect the channel 1, the yellow one, to the BOZ80, and the blue one, this is channel 2, to the SPA11. And then we can compare the output signals for both transistors regarding time delay related to the generator. Here we have the small test setup. This is the input from the generator, 50 ohms termination, 2 times 100 ohms in parallel. The two resistors, 470K, connected to the gate inputs of the both transistors. Here we have the 350 up to 400 volt DC coming out of the power supply. Now it is stable without load. Here we have 2 times 270K in the drain, and here we have the connection. High voltage probes, they are specified up to 2.5 kV. My smaller ones, but they are good enough for this purpose. And here it is a channel 3 which is connected to the input signal from the square wave generator. Here we have the input signal, approximately 10 millivolt times 10, it's 100 millivolt per division, so we have 50 millivolt. That's the same as we have set on the generator. It's a low amplitude signal. Here we have the output signal of the BOZ80, that's the yellow trace, and the blue one is the output signal of the SPA11. And we see when the input signal drops, the output signal of the BOZ80 rises very rapidly. We can say instantaneously. When oops, not too much. We can see there's absolutely no delay. Yes, the trigger makes a problem. There's no delay, and when the voltage goes up, then it drops down. Whereas on the SPA11, that was the BUZ80. On the SPA11 we have a considerable delay here between the falling input signal and the rising output signal. This is not so nice. The time delay, we have 10 milliseconds per division. This is approximately 10 milliseconds. So this may be the cause for the problem. This is a dead time. And the dead time in a loop controlled circuit is always deadly. This is the behavior of the small signal amplitude, and now I will increase the input signal, the amplitude, up to 1 volt or so. And now the behavior at the bigger input signal. We have approximately 2 volt and a little bit of DC offset, of course, which is needed to control the gates. And we see here again the yellow signal from the BUZ80 is earlier than the blue signal from the SPA11. On the falling side, when the voltage goes up, there is no big difference. So I think it is more or less parallel in the beginning, and here the SPA11 seems to be a little bit faster, but decisive is the reaction here on the top when the signal goes down in the small signal variations. That's important for the loop, and here we have a clear advantage of the old BUZ80. So my next test will be to replace the SPA11 on the Q5 in the voltage stabilizer, not the 4 transistors on the heatsink. They are only source followers. I think there will be not a so big problem, but we have seen that the transistor Q5, which is a voltage regulator, causes the problems with instability. I think we have identified one problem now. This is the source impedance which drives these 4 Mosfets. The source impedance is not only the 100K, it's also the transistor, this regulator transistor, and the drain resistance. The drain resistor is 540 kilo ohm, and depending upon the voltage output we have here also in the source drain of this transistor also some 100 kilo ohm. And we have seen when I increase the output voltage, suddenly we have instability. This means when we have here several 100 kilo ohms which are added in series with this 100 kilo ohm, then we get a problem. For test purposes I added 2 resistors, 3 times 56K in parallel. These are these, you see them. It is switched off now here. These 3 resistors in parallel to the existing 270K resistors, and when I switch on, make a reset, then we see I have a load of course connected. We have 200 volt output, this is more than we had before. So I think the problem is the source impedance, or the driving impedance of these 4 transistors due to the high capacity they have. So I think the solution will be to reduce this impedance here. We have seen that the reduction of the impedance could be a solution, but it isn't a solution. The problem still persists. It got a little bit better, but in general, depending upon the impedance of this transistor, whether we have a high or low output voltage, the output was not stable again, so we have to choose a different solution. One possible solution is to add another source follower instead of the low ohmic resistor to get a low source impedance, driving impedance for the 4 transistors. Again, it was a little bit better, but also it did not cure the problem totally. Depending upon the output voltage and the load, there were some oscillations. I swapped this capacitor C8 from here to here, made a connection from here to the gate, from here to here, added here another capacitor, I didn't get it stable. There was always an output voltage between 0 and 400 volt DC where it was unstable depending upon the load, and even with resistive loads it was not stable. And then when we imagine that we have in practice not only resistive loads, when we have capacitive loads or inductive loads, for example a tube amplifier with an AF transformer connected to the loudspeaker and so on, or we have a non-linearity of the tube, or a little bit a changing load, this circuit is also not the solution. And now what to do? Imagine you are driving a car, you see a traffic sign. On the traffic sign in big letters it is written dead end. What are you doing? You turn around by 180 degrees, drive back and search a new road. The same we have to do here. The idea to use power MOSFETs in the output, 4 in parallel as an actuator, the idea I think cannot be realized with a simple circuit like this. It would require a high sophisticated amplifier circuit with time constants adapted to the characteristic of the power MOSFETs. So the idea is now to replace the power MOSFETs by BJTs, bipolar junction transistors, or NPN as we call it, transistors, power transistors, not power FETs, simple power transistors. And this will be my next version of this high voltage power supply. I got cheap NPN power transistors. This is a type 2SD1555. Application is for color TV horizontal output applications. Okay, we do not have this application in our days today. But the transistor itself has rather good data. The collector output voltage or open emitter voltage is 1500 volt, more than sufficient. Open base also between collector and emitter. It is with open base it is 600 volt. So this transistor is good for our application. There is a small disadvantage. There's a resistor between base and emitter. I measured it with very low voltage, below the threshold voltage of the base emitter with 42 ohms. It seems to be a damping resistor. This can cause troubles, we will see. And another problem is the gain. The beta or the B is specified with 8 or higher. So the current gain is not very high. This wouldn't be a problem because the gain can be created anywhere else in the circuit. It's not necessarily in the transistor. So this could be an idea, and I realized now a new version with this transistor. This is now the next version I try. Again, 4 transistors in parallel. I don't need it for the current, but for the short circuit behavior, I think it is better. 10 ohm in the base in series. This transistor has a transit frequency of 3 megahertz. This could cause problems with oscillation, so 10 ohms in series is not so critical. And the 5th transistor here is an emitter follower to drive these 4 transistors. And then here we have the output, the Q7, the source follower which drives this one. We will see whether it is necessary to have both or not. And here is the voltage regulator as we had. So this circuit is now built. It is ready for testing. Here we have the new 4 output transistors. And here's the 5th one, it's the emitter follower to drive these 4 transistors. And here we have the source follower with a little heatsink. It's necessary because the current here is some milliamps. Let me say 10 milliamps maximum for maximum output, but the voltage drop may be 200 or 300 volts, so several watts are heated and dissipated here. This is not enough for this power, but for a short test it's okay, just to see whether it works. This transistor here transistors are mounted on the heatsink with thermal or heat compound, as you see. There are also protective diodes over the base emitter in reverse direction to protect the transistors against the reverse voltage. Okay, let's see whether and how it works. The power supply is connected to the mains, no load connected. The output is stable between 0 and this is 400 volt full scale, no current flowing. And then I connect the maximum possible load, 4 resistors, 2 kilo ohm in series and then parallel, so the total resistance here is again 2 kilo ohm. Each one has 25 watts as I see, so totally we have here 100 watt, at least for a short time. I connect it now and then watch the ammeter. Can increase the voltage, 100 milliamps, 200 milliamps. The voltage drops a little bit. Again, this is a consequence of a little bit too weak power transformer. But as we see, we have stable output, and when I remove it, plug it in again, same procedure at 400 volt. No fear, I'm careful. A little bit of drop, I assume it's a consequence of the hum in the power supply in the rectifier circuit. I will check it, but in general now it works. And I think this is a solution to replace the power Mosfets with the bipolar transistors. During testing and some measurements, I've seen that this emitter follower here is nearly useless. Why is it useless? Well, we have seen there is a parallel resistor between base and emitter, a very low ohmic base emitter resistor, which makes this emitter follower, which is a Darlington configuration with the other 4, nearly ineffective, and I will explain you why. Imagine we have here the 4 base connections of the 4 output transistors, and there is totally a current flowing 200 milliamps, and they have a current gain of 8 to 10. Let's calculate with 10. So we need totally 20 milliamps flowing into the 4 transistors, 5 milliamp per transistor. So we have here a current of 20 milliamps, and we have here only 42 ohms. So the voltage drop here when the current flows through this resistor is approximately 1 volt. This is sufficient, a little bit sufficient to make this transistor conductive, but it is not a complete Darlington transistor. Partially the resistor is conductive and partially the transistor is conductive. So it has no big effect. And I measured for 200 milliamps output an input current here of 10 milliamps on the base, which cannot be true because when we have assumption gain of 10 and also the transistors have 10, so we totally have a current gain of 100. So we should only have here a current of 2 or 3 milliamps, not more, but we have here 10. So the parallel resistor here makes a problem. And on the other hand, this transistor, the 5th transistor in the base connections of the other 4, which should be a Darlington effect, is completely useless. So my next try will be to delete this transistor and mount this fade on the heatsink here as a 5th transistor. Let's calculate the heat dissipation. This transistor has to supply approximately 10 milliamps for 200 milliamps output. 10 milliamps is within the specification of this transistor. The maximum voltage drop can be 400 volt when we have a low output voltage. 400 volt times 10 milliamps is 4 watt. This needs a little bit of heatsink, not big, but when I install this power Mosfet here as a 5th transistor on the heatsink, remove this one and install this one, then I can omit this transistor, and then we have only this one as a driver for these 4 transistors, and this should also work, and I will do it in the next step. Or to show it in the prototype, I will move this transistor, the source follower with a small heatsink here, and this place, this is a emitter follower, the Darlington type, which is not very effective. So I will place this one here and delete this one. I don't need it. And then I think it will be okay. The regulation transistor still is here. The voltage regulation is made with this one. Here is the trim pot in the source connector. I will replace it with a resistor of, I think 1 kilo ohm is okay. And this will be the new version, and I think this will be the last version which will operate. Keep your fingers crossed. This is the final solution. I hope it's a final solution now. We have the 4 NPN transistors in parallel, decoupled with the 10 ohms, 100 ohms 2 watt resistors as we had. In each base we have a protective diode against reverse voltage. That's important. By the way, there is a diode internally in this transistor, in each transistor, also in reverse direction, polarized like this diode. It is not shown in this diagram. I have to look for a better schematic, but at the moment I leave it. The 10 ohm resistors here are for damping, to prevent any oscillations, RF oscillations. And here we have the source follower, which is also mounted now on the heatsink. It's an over voltage protection, 12 volt, and reverse voltage also. Here we have a series resistor of 10 ohm, and here we have 10 kilo ohm. There is a reason for it to do it. This line from here to here is rather long and has some capacity to ground, and also to the other lines which are also fed in parallel. So I have also here a damping resistor with 10 ohms. Maybe it's not necessary. The 10 kilo ohm is on the other side, so this line here is approximately 15 centimeter. So I think it's not wrong to have here also a small damping resistor. That's the final solution. The rest is as it was. So this is a voltage regulation feedback, and maybe I will change these 2 resistors a little bit in value and make it a little bit lower, but in general it's not a problem. And here we have the mechanical construction. These are the 4 transistors, the big NPN transistors, and here in the center we have the power Mosfet, which drives the base connections of these 4 transistors. This pink one is the supply voltage, which is connected to the collectors and to the drain of the power Mosfet. The 4 light blue are the 4 emitters from the power transistors, and the gray line, which is this one, goes to the gate source or gate connection of this power Mosfet. I will install it as it was, and then we will see how it works. A short check whether the voltmeter is calibrated. We have here setting 10, it's 200 volt. With 20, it is a little bit difficult to set it, it's 400 volt. At 20, that's okay. And now we can connect the load. We have here the maximum load prepared for 400 volt. Each resistor has 2K in series and in parallel, so we have totally resistance again of 2K. Each has 25 watts, so we have 100 watt terminal capability. And when we increase the voltage, we will see the current also increases. I've checked the ammeter. 10 is 100 milliamps. You're a little bit more concentrated to it. So at 200 volt we will have 100 milliamps. That's 2 kilo ohm. And at 400 volt we have 200 milliamps. I cannot increase the voltage more because there's a little bit of hum. I show it on the scope. We see here the output voltage, that's the 0 line, and the center is 400 volt. When I increase the output voltage, again with full load, so we see there's a small ripple on it. I cannot avoid it because the charging capacitors and the line voltage is not high enough. When I increase the line voltage a little bit, up to 250 volt. Gets a little bit better, I get more output. But now I have an input voltage, line input voltage of 250 volt AC. That's a little bit too high, I go down. My variac is tuned. In principle it works. Now I will try a low ohmic load and to see what's the output when we have a very low ohmic load with full current. We have connected 100 ohms. Yes, it's 100 ohm. I think 25 watt or so. 100 ohms, maximum 200 milliamps, that's 20 volt. We will see nearly no voltage. In this case, I have one problem, the overcurrent protection does not work. I don't know what the problem is. Some hours ago I had a bad short circuit. It was my fault. Maybe the sensor was killed. I have to look for it again. There's not enough output current, so maybe there's something wrong. I can go up to 220, 230 milliamps, which is not intended, but that's a minor topic. I will clear it, I will check it. And nearly I had forgotten to tell you that the actual schematic version 0.9.6, which is this version actually working, is on my homepage. The link is in the description of the video. With this footage we are now at the end of part 7. We have seen we had to change the concept. We had to delete the power MOSFETs and the output in the actuator and replace them by BJTs, bipolar junction transistors, which was much better and gave us the stability we require. Obviously the power MOSFETs with the high gate source capacity are not good for closed loop circuits. It would require to have a dedicated time constant in the voltage comparator to compensate it. So it's too difficult, and the problem is a big setting range of the output voltage and the current range between 0 milliamp and 200 milliamp. So we have an output between 0 and 80 watts at various voltages and currents, and maybe there's always a bias or an amplification factor which creates oscillations. So the BJTs are the much better solution. I will finalize the project. In part 8 we will see how it works, so we do the fine tuning, and then the next step will be to produce a PCB. Anyhow, stay tuned, stay healthy, see you on this channel.